Something came from beyond the stars and into our solar system. It is not science fiction and not a thought experiment. It is a real visitor, right now, cutting through our cosmic backyard. 3 days ago, NASA called an emergency press conference about it. Not routine, not scheduled, emergency. What they showed looked like a comet, yet raised more questions than answers. Tonight we are going to unpack what they revealed and what they left unsaid. Tap like, subscribe, and come with me into this mystery. The visitor has a name that sounds almost ordinary for something so strange. Astronomers call it 3I Atlas. On paper, it is a comet. Ice, dust, rock, a frozen relic from the birth of a distant star system. In reality, it is only the third confirmed object ever seen entering our solar system from interstellar space. The first was Oumuamua in 2017. The second was Comet 2I Borisov in 2019. 3I Atlas is number 3 on that list, and from the very beginning it refused to behave like a simple repeat of the last two. When NASA steps in front of cameras, it usually does so on a schedule. Missions are planned years ahead. Press briefings are polished and predictable. On November 19, 2025, the mood was different. Officials described this as an emergency update. The topic was narrow yet huge in implications. Images of 3I Atlas taken near its closest approach to the Sun, the moment when the comet was supposed to show its true nature. The paradox was simple. At that critical moment, Earth itself was in the worst possible place. On October 29th, the date of perihelion, our planet sat on the opposite side of the Sun from the comet. Imagine the Sun as a blinding spotlight in the middle of the stage. Earth was backstage, blocked out, unable to see the main act. Every ground-based telescope, every Earth-orbiting observatory, every backyard astrophotographer was effectively blind. If we had only relied on our home world, we would have missed everything that mattered most about this interstellar encounter. At least that is what most people assumed. NASA revealed that this was not the whole story. Earth was in the dark, but humanity was not. While our planet hid behind the Sun, Mars was perfectly placed with a clear view of 3I Atlas at perihelion. And Mars was not alone. Orbiters circling the red planet, a rover on its surface, and multiple spacecraft sprinkled through the inner solar system had already been quietly retasked. They were turning their cameras and spectrometers toward a single, moving point of light. A surprise guest from another star system had suddenly become the main priority for a whole network of machines. At the press conference, NASA officials walked through this coordinated campaign with a kind of calm pride. They showed visible light images from the Mars Reconnaissance Orbiter. They described ultraviolet measurements from the MAVEN mission. They showed frames of 3I Atlas drifting through the fields of view of solar observatories. The message was clear. Even though Earth was blocked, we still managed to capture the closest images ever taken of an interstellar object. For most space agencies, that would be the end of the story. We did it. Mystery solved. Instead, something in the tone caught people's attention. During the briefing, Amit Kshatriya, a senior NASA official, paused to do something unusual. He said he wanted to address the rumors. He stated firmly that this object is a comet, that it looks and behaves like a comet, and that all the evidence points to it being a comet. On the surface, that sounds reassuring. Underneath, it raises an obvious question. Why did he need to say that at all? When was the last time a press conference about a normal comet had to calm down speculation about what it really is? That choice of words echoed across social media and scientific circles. Address the rumors. Evidence points to it being a comet. Careful phrases like that are scientifically correct, yet they leave a crack open in the door. It almost sounded as if NASA was talking past someone, trying to stay ahead of a story that was growing outside the room. Because in the weeks before the press conference, something else had been happening. Papers, blog posts, and interviews from respected scientists were quietly asking whether 3I Atlas might be more than just another ball of ice and dust. Then came the second twist. Not only had NASA already seen 3I Atlas at its most active moment, they announced that on December 19th, the comet would make its closest approach to Earth. About 170 million miles may not sound close in everyday terms, yet in astronomy, that is a near miss. Ground-based telescopes will be able to gather fresh data. Skilled amateurs with serious equipment might even capture their own images. For the first time since this visitor entered our solar system, Earth will have a clean line of sight. So part 1 of our story leaves us with a layered puzzle. We have a rare interstellar comet, a global blind spot at the moment of maximum drama, a secretive rescue plan using spacecraft scattered across the solar system, and a nervous space agency going out of its way to insist that everything is completely normal. In the next part, we will rewind to the night 3I Atlas was first found and see how this whole chain of events began long before anyone stepped up to a microphone. To understand why this comet became such a big deal, we have to go back to the night it quietly entered our databases as nothing more than a moving smudge. It was July 1st, 2025, at the Atlas survey, the Asteroid Terrestrial Impact Last Alert System. Atlas is a kind of planetary smoke detector. Its telescopes sweep the sky every clear night, taking rapid-fire images, feeding them to software that hunts for anything that shifts against the fixed background of stars. Most of what it finds are harmless rocks, old regulars, known comets coming back on schedule. On that night, one of those moving dots refused to behave. The software flagged a new object. That alone is not unusual. New asteroids are discovered all the time. But when astronomers started running preliminary orbit calculations, the numbers came back wrong in a very specific way. The path was not an ellipse, not even a stretched one. It was open, hyperbolic. That is the mathematical way of saying this thing was moving too fast, ever to be trapped by the gravity of our Sunday. Hyperbolic orbits are a smoking gun. If the speed is above escape velocity, the object is not a long-lost member of our own family of planets and comets. It is a passerby from deep space, cutting through the solar system once, and then vanishing back into the dark. That is exactly what we saw with Oumuamua in 2017. The first interstellar visitor, a flattened or elongated chunk that flashed through before we really understood what we were looking at. Then in 2019 came Comet 2I Borisov, which soothed everyone by behaving like a textbook dirty snowball from another star. Within days of the Atlas alert, observatories around the world turned their attention to the newcomer. The Minor Planet Center began collecting positions from professional and amateur telescopes and refined the orbit. With each new data point, the picture sharpened. This was not a near-miss asteroid from the main belt. This was not a lazy long-period comet simply paying another visit. The calculations hardened into a single conclusion. We were watching the third confirmed interstellar object ever detected entering our solar system, 3I Atlas. At first, you could feel the relief in the way people talked about it. After all the arguments over Oumuamua, maybe this one would be simple. A nice, bright comet from another star system. Plenty of time to watch it. Clean data, no drama. And in some ways, that is how it started. Early images showed a growing coma, the fuzzy atmosphere of gas and dust around the nucleus, a tail forming as sunlight pushed material away. On the surface, that all looked comfortingly normal. Then the details started to pile up. 3I Atlas did not match Borisov. It did not quite match our catalog of homegrown comets either. It was big, probably several kilometers across, yet strongly active far from the sun, at distances where most comets are still half asleep. The brightness did not ramp up the way standard models predicted. The pattern of outgassing suggested a surface that was anything but exhausted, which is odd for an object that should have been bombarded by radiation in deep interstellar space for millions or billions of years. Astronomers use models like mental templates. You feed in size, distance, composition, and you get an expected level of activity. 3I Atlas kept slipping out of those expectations. Some researchers proposed that maybe it was a relatively fresh ejection from its birth system, a young exile, rather than an ancient wanderer. Others wondered if we were simply underestimating how much volatile ice could survive in deep space. Even in those early weeks, you could feel people stretching their theories to keep this thing inside the comfortable box labeled natural comet. And then came the geometry problem, the twist that turned a purely scientific curiosity into a logistical headache. As the orbit was refined, it became clear that perihelion, the moment of closest approach to the Sun, would fall on October 29, 2025. Perihelion is when a comet goes into overdrive. Ices flash into gas. Jets roar from the surface. Tails bloom and stretch for millions of miles. If you want to understand what a comet is really made of, you want spectra and images from that exact window. Miss it, and you are stuck with an incomplete story. When astronomers checked where Earth would be on that date, the answer was brutal. We would be on the far side of the Sunday, completely wrong side of the stage. Our most powerful optical telescopes, our biggest infrared observatories, even many space-based instruments in Earth orbit would be effectively blinded by glare. For a while, it looked as though we were about to live through the same frustration we had with Oumuamua, another interstellar visitor blazing through its most revealing moment while we stood in the dark. Inside that problem, though, was an opportunity. Because our solar system is not just Earth and its satellites anymore. We have outposts, eyes and ears scattered across millions of miles, Mars orbiters, a rover in Jezero crater, solar observatories floating in special orbits, asteroid missions cruising through the inner system. As soon as scientists realized Earth would be blind, people started to ask a different question. If we cannot see 3i Atlas from here, who can? That question is what eventually led to the emergency press conference, the solar system-wide observing campaign, and the strange tension you could feel in the room when NASA insisted this was nothing more than a comet. In the next part, we will ride along with the spacecraft that became our remote eyes, from Mars Reconnaissance Orbiter to Perseverance looking up from the Martian surface, and see what this visitor looked like from everywhere except Earth. When it became clear that Earth would be blind at the moment of maximum drama, the question shifted from disappointment to strategy. If we cannot see 3i Atlas from here, who can? The answer was hiding in plain sight on the next planet over. Mars was sitting in almost the perfect spot, with a clear view of the comet as it whipped past the Sunday. And Mars was not empty. It was surrounded and occupied by machines we had already sent. Think about that for a second. The same species that once thought of Mars as a mysterious red dot now has an entire toolkit of spacecraft there. Orbiters circling the planet, a rover trundling across an ancient lake bed. Instruments that were designed for completely different questions suddenly became our best chance to watch an interstellar visitor at close range. The geometry that cursed Earth turned Mars into the front row. The star of that Martian fleet is the Mars Reconnaissance Orbiter, often shortened to MRO. It has been looping around Mars since 2006, patiently mapping the surface in absurd detail. Its high-resolution camera can pick out objects the size of a desk. Usually it stares down at dunes, canyons, and rover tracks. On October 2, 2025, controllers gave it an unusual order. Turn away from Mars, point into deep space. Look for a faint, fast-moving speck. 19 million miles separated MRO from 3i Atlas that day. In cosmic terms, that is practically breathing on it. For the first time in history, a spacecraft got a high-resolution, optical view of an object that was born around another star. The image did not show a crisp rock with craters. At that distance, the nucleus was still wrapped in a glowing shroud of dust and gas. But you could see structure, a bright central condensation where the solid core hid, swelling into a blurry cocoon that marked the inner coma. Getting that image was not easy. The comet was moving against the background of stars. Exposure times had to balance faintness against motion blur. Engineers had to repurpose a camera designed to photograph a stationary planet and use it like a telephoto lens on a race car. When the picture came down, it was more than a pretty snapshot. It was proof that human-built machines could pivot on the fly to capture a once-in-a-century opportunity. While MRO watched invisible light, another Mars mission provided a view our eyes cannot see. The Mars Atmosphere and Volatile Evolution mission, known as MAVEN, carries an ultraviolet spectrograph. Its day job is to study how Mars lost most of its air over billions of years. In late September, MAVEN stopped staring at the thin Martian sky and turned toward 3I Atlas. In ultraviolet, the comet exploded into a different kind of brightness. What MAVEN saw was a vast hydrogen envelope surrounding the comet. Hydrogen is the lightest element in the universe. It streams away from the comet as sunlight breaks apart water molecules. You cannot see this with ordinary cameras. In ultraviolet, it glows like a ghostly halo, far larger than the visible coma. MAVEN's data showed a hydrogen cloud consistent with water ice boiling straight into vapor. That matters. It confirms that this visitor from another star is rich in the same water that covers Earth and once flowed on Mars. It means some of the ingredients for life are not unique to our system. They are packed into the deep freeze between stars. Down on the surface, the Perseverance rover was in the middle of its own mission, hunting for signs of ancient microbes in Jezero crater. Its cameras are tuned for rocks, soil, and the nearby sky. Yet on several nights in October, controllers asked it to do something strangely human. Look up. Capture the sky of another world with an interstellar comet passing overhead. The images from Perseverance do not show a dramatic movie comet with a sweeping tail. They show a bright point etched into the Martian night with a faint extension in the direction away from the Sunday Simple, almost underwhelming at first glance. Until you remember what you are looking at. A robot on a planet that might once have had its own oceans, taking a picture of an object from another star system as it rushes through our own. Two different chapters of cosmic history intersect in a single frame. Mars was only one node in a much bigger web. Closer to Earth, the Punch mission, whose full name is Polarimeter, to unify the corona and heliosphere, had its cameras trained on the space around the Sunday Punch is, designed to see how the hot outer atmosphere of the sun connects to the solar wind, the stream of charged particles blowing through the solar system. Its wide-field instruments also picked up 3I Atlas, gliding through that flow. Punch did not just take still photos. It recorded sequences. Frame after frame of the comet moving against the stars, its tail breathing and twisting as gusts of solar wind washed over it. That kind of movie lets scientists see how dust and gas respond to the invisible environment around the Sunday. The comet becomes a tracer particle, mapping the wind that we cannot see. Then there is the Solar Terrestrial Relations Observatory, known as STEREO. Two spacecraft, placed in different orbits around the Sun, give a kind of stereo vision of solar events. Both saw 3I Atlas in their coronagraphs, instruments that block the bright disk of the Sun so that the faint corona becomes visible. In those views, the comet is a tiny intruder, slipping through the Sun's outer atmosphere while streams of charged particles roar past. Watching over all of this is a veteran. The Solar and Heliospheric Observatory, usually called SOHO, has been staring at the Sun since 1995. It has discovered thousands of comets that dive toward the Sun and disintegrate. Many never had names before SOHO spotted them. 3I Atlas is different. It is not a local snowball making a final plunge. It is a traveler from another system, bright and solid enough to stand out clearly in SOHO's instruments as it swings through perihelion and survives. Its tail stretches for millions of miles, sculpted by sunlight and solar wind into a long, luminous blade. Even missions that had nothing to do with comets joined in. The Lucy spacecraft, on its way to the Trojan asteroids near Jupiter, grabbed a snapshot as geometry allowed. Psyche, heading toward a metal-rich asteroid between Mars and Jupiter, did the same. Each image is a small data point, another angle on the same visitor. Put together, these viewpoints turn the solar system into a loose, improvised observatory, with baselines measured in hundreds of millions of miles. This is what NASA wanted to showcase at the press conference. A story of ingenuity, coordination, and a little luck. A solar system-wide camera network turning toward one target because we refuse to let a rare interstellar visitor slip past unseen. Yet woven into that triumphant narrative is a quieter question. If this is just a normal comet, why are so many scientists losing sleep over the details? In the next part, we will go back into that briefing room, listen carefully to what the officials said on stage, and notice the strange gaps where they did not quite finish their sentences. Back in the briefing room on November 19th, the story looked simple on the surface. You had the classic NASA stage setup, a dark backdrop with a glowing image of the comet, a row of microphones, a few carefully chosen scientists and managers in front of cameras. The public message was clear. We did something heroic. Even with Earth blind at perihelion, our spacecraft across the solar system pulled off an incredible observing campaign. Nikki Fox, from the Science Mission Directorate, played the role of narrator for that triumph. She explained how 3I Atlas passed inside the orbit of Mars, how that placement turned the red planet into a prime viewing platform. She talked about coordination, about using every available asset. It was the kind of story NASA loves. Ingenuity, planning, a universe that happens, for once, to line up with our hardware. Tom Statler, the lead scientist for small bodies, added the emotional punch. He described the community as really excited about these new observations. You could hear that he meant it. For people who study comets and asteroids, this is the dream case. An interstellar object, bright enough, close enough, with enough instruments pointed at it to generate rich data for years. On stage, excitement was the official mood. Then Amit Kshatriya spoke, and the tone shifted. He said he wanted to address the rumors. That phrase landed like a small thunderclap. Rumors about what? Why bring that up in a formal press briefing? He went on to say that this object is a comet, that it looks and behaves like a comet, and that all the evidence points to it being a comet. Scientists watching could hear the careful phrasing. Evidence points to, not absolute certainty, not a closed door. This way of speaking is normal inside science. You almost never hear a researcher say absolutely, never, impossible. They say the data are consistent with. They say the best explanation is, that is good practice, it is honest. Yet it is also unusual to see NASA spend precious minutes of an emergency briefing on reassurance, reiterating that everything is natural. Nobody felt the need to do that with Comet 2I Borisov. Nobody called a press conference to insist that Hale-Bopp was not a spaceship. So why now? Why this object? In the weeks leading up to the briefing, speculation had already started to swarm. Oumuamua opened that door in 2017. Its strange acceleration and lack of visible outgassing planted a seed in the public imagination. When the third interstellar visitor showed hints of weirdness, YouTube channels, blogs, and even some researchers began asking pointed questions. Could there be something more going on with 3I Atlas? Are we looking at a natural fragment or a probe? NASA found itself in a delicate position. On one side, there was genuine scientific curiosity. Astronomers are trained to poke at anomalies, to doubt easy answers. On the other side, there was a rising wave of wild claims online. Alien megastructures, secret government contact, unlimited energy technologies hidden in the tail. None of that was supported by data, but the buzz was loud enough that reporters were already asking about it. So Kshatriya walked a tightrope. Acknowledge that rumors exist without repeating them. Affirm that the object behaves like a comet without claiming a level of certainty the data do not truly support. Reassure the public that NASA is on top of this without feeding conspiracy thinking. It is a hard needle to thread. If you say nothing, people accuse you of hiding the truth. If you say too much, you sound defensive. Nikki Fox's part of the briefing stayed comfortably in safer territory. She talked about the geometry that made this event special, the comet crossing inside Mars' orbit, the position of the solar observatories, the fact that missions like Punch and Stereo could watch the encounter in real time. She emphasized the scientific opportunity and downplayed anything that smelled like controversy. What they saw, not what those observations might mean for the wilder theories. Statler did something similar. He highlighted the scale of the dataset, the closest images ever taken of an interstellar object, ultraviolet spectra that trace water from another star system, time-lapse movies of a comet tail being sculpted by the solar wind. He did not spell out the ways in which 3I Atlas deviates from standard comet behavior. High activity, far from the Sunday strange coma shape, complex tail structure. Those details stayed between the lines. During the question period, a few reporters tested the boundaries. They asked directly about the speculation. Is there any chance this is artificial? Are you ruling out non-natural explanations? The answers were polite, careful, and repetitive. The panel stressed that all current measurements support the comet interpretation, that no evidence suggests anything engineered, and that extraordinary claims demand extraordinary proof. Each time, they brought the conversation back to the safe harbor of natural processes and the beauty of the data. For a casual viewer, the briefing might have felt straightforward. A rare comet from another star. Amazing images. Scientists thrilled. Story over. For anyone listening closely, there was another layer. The way rumors were mentioned but never named. The way anomalies were implied but not explored. The way the word comet became a kind of shield, repeated often enough to act as a spell against uncomfortable possibilities. That tension is what caught the attention of one particular astronomer who has built a reputation on asking the questions others would rather leave alone. He watched the same briefing you just walked through. He heard the same careful phrases. Then he sat down and wrote an article with a deliberately provocative title. In the next part, we will meet Avi Loeb, trace his history with troublemaking ideas, and see why 3I Atlas has him once again challenging what everyone thinks is obvious. When NASA finished its careful performance on stage, another voice stepped into the spotlight from a very different venue. A written essay with a sharp title began to circulate among astronomers and science readers. It came from someone who has become almost synonymous with cosmic controversy, Avi Loeb. For people outside astronomy, his name might sound like just another talking head. Inside the field, he is harder to dismiss. Loeb is not a random outsider with a telescope in his backyard. He is the former chair of the astronomy department at Harvard. He has published hundreds of peer-reviewed scientific papers. He has advised NASA and served on national committees that shape the direction of space research. He has supervised students who are now leading their own observatories. Agree with him or not, you have to engage with him. When he raises questions, the community feels pressure to answer them. In response to the 3I Atlas press conference, he wrote an article with a pointed theme: the idea that nothing is more deceptive than an obvious fact. At first glance, the statement sounds like a paradox. How can something obvious be deceptive? That is exactly his point. When a conclusion feels obvious, when everyone nods and says, "Of course it is just a comet," you risk blinding yourself to the data that do not fit as neatly as you wish they did. Loeb makes it very clear that he is not claiming 3I Atlas is definitely artificial. He is not shouting that it is a spacecraft. Instead, he does something more uncomfortable. He reminds everyone how many times in the history of science the obvious answer turned out to be wrong. He argues that the job of a scientist is not to eliminate weird possibilities by instinct, but to test them and rule them out or keep them alive based on evidence. To understand why this matters, we need to rewind once more to Oumuamua in 2017. That first interstellar object looked nothing like a standard comet. There was no visible coma, no tail in deep images. Yet as it swung around the sun, its motion did not quite follow the path dictated by gravity alone. It experienced a gentle push, as though tiny rocket engines were firing. The standard explanation was outgassing from jets too faint to see. Loeb pointed out that the acceleration was unusually smooth. Instead of jittering the way you might expect from random jets switching on and off, it behaved like a continuous pressure. He also noted that if the energy came from normal outgassing, The object should have lost mass and changed its spin in detectable ways. Add to that the odd, elongated shape inferred from its changing brightness, and you had a package of anomalies that did not slot neatly into any existing category. His suggestion was simple but explosive. Maybe this was not a rock at all. Maybe it was a thin, broad object pushed by sunlight like a light sail. In other words, maybe we had just seen something made rather than born. The reaction was swift. Many astronomers accused him of reaching for aliens too quickly. They argued that natural explanations, however strained, were still more likely than a technological origin. Journals filled with models that tried to describe Oumuamua as a fragment of nitrogen ice, or a fluffy fractal dust ball, or some other exotic yet unengineered thing. Then came 2I Borisov in 2019 and seemed to calm everything down. Borisov behaved exactly like a classic comet. It had a bright coma, a clean tail, and a chemistry that matched the kind of icy bodies we know from the outer regions of our own system. For many scientists, Borisov was the comforting confirmation they needed. Interstellar objects are real, and they are just comets and asteroids shaken loose from their home systems. Oumuamua, they decided, was probably a comet after all. Unusual, yes, but not worth rewriting physics for. Loeb did not forget Oumuamua, but the mainstream conversation cooled. Then 3I Atlas arrived. It lit up early. It seemed too active for something that had supposedly spent eons freezing in interstellar space. It developed a strange teardrop, coma. It showed complex tails and hints of odd chemistry. To most astronomers, this meant exciting new data on a natural object. To Loeb, it looked like history trying to repeat itself. In his article, he draws a straight line between the treatment of Oumuamua and the rush to label 3I Atlas a normal comet. He asks whether the community is once again smoothing over anomalies because a simple story is more comfortable. If you already believe interstellar objects are harmless chunks of ice and rock, you start every analysis with that conclusion in your head. Confirmation bias does the rest. You focus on the ways the data match a comet model, and quietly ignore the ways they do not. He points to specific issues. The unusually vigorous activity despite an ancient journey. The hyperbolic path that just happens to line up perfectly with our most capable observatories. The mix of features that resemble both past interstellar objects and rare edge-case comets. He does not claim that any one of these proves anything artificial. Instead, he asks how many coincidences we are willing to stack up before we admit we might be missing something. This is exactly the kind of argument that makes many scientists roll their eyes while secretly double-checking their numbers. On one hand, nobody wants to be the person who cries alien every time a data set looks messy. On the other hand, nobody wants to be the person who ignores a genuine signal because they were too afraid of seeming foolish. Loeb is comfortable living in that tension. He would rather be wrong in an interesting way than quiet in a safe way. Even if you disagree with his conclusions, his presence changes the conversation. It forces NASA and the broader community to tighten their language, to back up claims with harder numbers, to say exactly why they think 3I Atlas is natural and where the limits of their confidence lie. That discomfort is useful. It pushes the science forward. So now we have two narratives, running in parallel. The official story of a comet from another star observed by a heroic fleet of spacecraft, and the unsettling counterpoint from a respected astronomer who says, slow down, look harder, and do not let obvious facts seduce you. In the next part, we will step away from personalities and pick apart the anomalies themselves, from the comet's surprising activity to its suspiciously well-timed path through our solar system. By now, you have heard the two competing storylines. NASA says 3I Atlas is a comet that happens to be in the right place at the right time. Avi Loeb says careful, obvious facts can be traps. To move beyond vibes, we need to look straight at the anomalies themselves. What about this object makes serious scientists tilt their heads and frown at their spreadsheets? Start with something deceptively simple. Size. 3I Atlas is not a tiny chip of rock. Based on how bright it is and how much dust it throws off, estimates put the nucleus at several kilometers across. Think of a city-sized chunk of ice and rock. That matters, because size changes the entire story of how it lives and how it dies. An object that big has had a long history. If it really spent millions or billions of years drifting between stars, its surface should be cooked by cosmic rays. The outer layers would be darkened, chemically altered, and stripped of the easiest to evaporate ices. Astronomers expect old interstellar comets to be crusty and reluctant. When they finally approach a new star, they should wake up slowly. 3I Atlas did not get that memo. It became active while it was still far from the sun, at distances where many homegrown comets are barely starting to stir. Telescopes saw a coma forming early, long before perihelion. The rate of brightening did not follow the gentle curve predicted by simple energy balance models. The comet started acting like a seasoned performer long before the spotlight was at full power. That early, activity means fresh, volatile material near the surface. A lot of it. You do not get a big bright coma and complex tails without significant gas and dust pouring off. One way to reconcile that with the idea of an ancient traveler is to imagine that much of the surface was somehow protected until now, maybe buried under a layer that has only recently cracked. Another way is to suggest that this is not ancient at all, that it was ejected from its home system relatively recently on cosmic timescales. But that raises a second puzzle. Ejecting small debris from a planetary system is easy. Planets like Jupiter in our own system act like gravitational slingshots, flinging countless icy fragments into interstellar space. The larger the object, though, the more stubborn it becomes. A chunk, several kilometers wide, carries a lot of inertia. You need a very energetic event, or a very specific planetary dance to kick it fully free of its star. So in one corner, you have the crust problem. An ancient traveler should be dead on the outside, yet this one is roaring. In the other corner, you have the ejection problem. A young exile that still has fresh ice near the surface requires a dramatic mechanism to get launched so hard. Both possibilities are technically allowed. Neither sits comfortably in the middle of our standard models. Then there is the path 3I Atlas took to get here. Interstellar space is three-dimensional. A visitor could approach from almost any direction. It could plunge in steeply above the plane of the planets or skim down below it. Instead, this object arrives on a trajectory that hugs close to the same plane where our planets orbit. Even more convenient, it sweeps inside the orbit of Mars, at a time when Mars is offset just enough to have a perfect view, while our fleet of solar observatories near Earth also have clean sightlines. On a whiteboard, you can absolutely treat that as luck. Random interstellar trajectories exist in all orientations, but we are far more likely to detect the ones that head into regions where our telescopes happen to be looking. That is selection bias. If you only listen where you have microphones, you hear the sounds that pass by those microphones. Statistically, some of those sounds will arrive at oddly perfect moments. Loeb does not deny the role of chance, but he asks whether we are being honest about how precise this choreography looks. 3I Atlas did not just wander somewhere near the inner solar system. Its path threaded a needle that put it close to Mars when Mars was heavily instrumented, and near the Sun when a suite of solar missions were operating in top form. If you were planning a mission to study a planetary system remotely, that is almost the exact path you would choose for your probe. Most astronomers counter with a different kind of probability argument. They point out that we are telling this story after the fact. Out of all the possible visitors that might pass through, we only write multi-hour documentaries about the ones that line up with our instruments. That is the same cognitive trap that makes lottery winners think their choice of numbers was special. The winning ticket always looks impossible once you focus on that one outcome. This is where the conversation stops being purely about numbers and starts to touch on psychology. NASA, as an institution, is strongly motivated to treat these alignments as lucky breaks. That lets them celebrate the cleverness of their engineers and the value of keeping many missions alive around the solar system. Loeb is motivated in a different way. He wants the community to hold itself to a higher bar before declaring something ordinary. Both instincts are human. Both can influence how we weigh the same data. Put the size, the surprising activity, and the finely tuned path together, and you get an anomaly list that does not scream artificial, but also does not whisper boring. Each item has a natural explanation. Crusts can crack. Big objects can be ejected. Trajectories can be lucky. Yet when you stack them, the picture starts to shimmer a little. You feel the urge either to shrug and say coincidence, or to lean forward and say, hang on, what else is going on here? That urge becomes even stronger when you stop looking at orbits and brightness and start looking at the comet's body language in light. In the next part, we will shift from dynamics to appearance, from paths to shapes and colors, and explore the strange chemistry, teardrop coma, and multi-tailed ghostly structure that make 3I Atlas look both familiar and deeply alien at the same time. So far, we have talked about paths and timing and lucky geometry. Now we need to look at what 3I Atlas actually is in light. Not where it goes, but how it glows. Because here the story gets even stranger. The more carefully astronomers stare at this thing, the more it looks like a comet from a parallel universe. Familiar enough to recognize, alien enough to bother you. One of the sharpest looks came from an old champion. The Hubble Space Telescope turned toward 3I Atlas in late July when the comet was still about 277 million miles from Earth. At that distance, you might expect nothing more than a fuzzy blob. Instead, Hubble revealed structure. Around the hidden nucleus was a cocoon of dust that was not round. It had a distinct teardrop shape, wider on one side, tapering to a point on the other. That shape is a clue. If a comet simply warms up and evaporates evenly, gas and dust should spread in all directions and form a mostly circular coma. Asymmetry means the outgassing is lopsided. Certain regions of the surface are blasting material into space. Other regions are quieter. In 3I Atlas, the bright part of the cocoon seems offset, pulled toward one side. That points to jets. Focused plumes erupting from specific patches, rather than a gentle haze from everywhere at once. Jets themselves are not weird. Many comets have them. Picture a dirty snowball with vents. Sunlight hits one face. Ices inside pockets suddenly vaporize, and gas blasts through weak spots, dragging dust with it. Over time, these jets can push on the nucleus like tiny thrusters and even change its rotation. What is unusual with 3I Atlas is how early this pattern showed up. Hubble saw this teardrop cocoon months before perihelion, at a time when many comets are still quiet. Fast forward to mid-November. An astrophotographer in New Mexico named Satoru Murata captured an image that quickly spread through the astronomical community. In his picture, 3I Atlas does not just have a single smoky tail. It has long, well-defined streaming structures, multiple tails fanning out from a core wrapped in a distinctly green coma. It looks almost theatrical, like a special effects artist decided to show off. That green glow is not just pretty, it is diagnostic. It comes from a molecule called diatomic carbon, two carbon atoms bound together. When sunlight hits larger carbon-bearing compounds in the comet's ice, it breaks them apart. For a brief time, diatomic carbon exists and emits light at specific wavelengths that our eyes perceive as green. The molecule is unstable. It survives only a few days before breaking down further. So a vivid green coma means active chemistry right now, not ancient residue. Lots of comets show some green. On 3I Atlas, the color is particularly intense. It is a chemical shout across space. It says, this nucleus is loaded with complex carbon compounds, and sunlight is tearing them apart at a furious rate. For scientists, that is a thrill. This is material that formed in the disk around a completely different star, now glowing in our sky in familiar shades. It suggests that the basic building blocks that feed into organic chemistry repeat themselves all over the galaxy. Look closely at Murata's image, and you can tease apart at least two different tails, possibly three. One is the dust tail. Made of tiny solid particles pushed gently by sunlight, it tends to curve, tracing the comet's orbit like a glowing trail of breadcrumbs. Another is the ion tail. This one is made of charged gas, which feels the magnetic field carried by the solar wind and points more directly away from the sun, often straighter and narrower. Some comets also grow a third tail from sodium atoms, which can appear offset again. Multiple tails are not unique to 3I Atlas, but they are rare enough that when you see them clearly separated, you pay attention. Each tail responds differently to forces in the solar system. Together they act as sensors, revealing the balance between radiation pressure, magnetic fields, and the comet's own outgassing. The complexity here tells you this is not a quiet rock slowly steaming. It is a dynamic, chaotic system throwing different kinds of material into space at once. Spectrographs add another layer. When astronomers spread out the light from 3I Atlas into a rainbow and measure the brightness at each color, they see the usual suspects: water vapor, carbon compounds, fragments of other common comet ingredients. That is part of why NASA can confidently call it a comet. Yet mixed in with the familiar fingerprints are features that do not perfectly match standard comet chemistry. Lines that are stronger or weaker than expected, ratios that feel off compared to our catalog of local icy bodies. On their own, those quirks might simply tell us that this comet was born in a different nursery. Protoplanetary disks around other stars can have slightly different element mixes. The temperature at which ices condense can shift. The timing of when gas is blown away can change. All of that can lead to comets whose chemical recipes are skewed compared to ours. In fact, seeing those differences is part of the scientific prize. It is a way to sample another solar system, without leaving home. Loeb and others push on a different part of that picture. They ask how far you can stretch the word unusual before it stops meaning natural. At what point do spectral oddities stop being just chemistry from a different star and start hinting at something processed or refined? The honest answer right now is that we do not know. The resolution of our instruments at these distances is limited. We are reading the barcode of an object dozens or hundreds of millions of miles away. We see the pattern, but not the fine print. Still, when you put the green coma, the early asymmetric jets, the multiple tails, and the slightly off-kilter spectrum together, 3I Atlas starts to look like a mashup. It is clearly comet-like. It has a nucleus, a coma, tails shaped by sunlight and solar wind. Yet at every level, it seems to push right up against the edge of our models. More active, more structured, more chemically interesting than an average comet has any right to be. For most astronomers, that is exactly what makes it exciting. A natural object that forces you to update your understanding. For a minority, it keeps the door cracked for more exotic ideas. Both groups agree on one thing: we need more data. And that is where the calendar comes back into focus. In the next part, we will look ahead to the December close approach, the battery of tests that Earth-based observatories are preparing, and how those measurements could either gently collapse this mystery back into the comet box or blow it wide open. Now we jump from what has already happened to what is about to happen. December 19th is circled on calendars and observatories all over the world. On that date, 3I Atlas will make its closest pass by Earth on this visit. It will still be out at roughly 170 million miles. Nowhere near any danger, but close enough for our best telescopes to really get to work. For the first time since this interstellar visitor was discovered, our planet will have a clear, unobstructed line of sight. Do not expect a Hollywood sky show. You will not walk outside, look up with your naked eyes, and see a blazing green sword across the stars. Even binoculars will not be enough. This is still a faint object against a dark background. But for serious amateurs with good equipment and for professional observatories, December is the payoff. An 8-inch telescope or larger, under dark skies, with careful tracking and long exposures, should be able to tease it out. Giant professional mirrors will go far beyond that, breaking its light into intricate fingerprints. The number one goal for many astronomers is spectroscopy. That is the art of taking the comet's light and spreading it into a rainbow so fine that every kind of atom and molecule leaves its own little notch or spike. We already know 3I Atlas carries water and carbon compounds. December's spectra should reveal the ratios in much more detail. One of the most important numbers will be the balance between heavy hydrogen, called deuterium, and normal hydrogen in the comet's water. That ratio acts like a fossil thermometer, telling us how cold it was where the ice first formed. If that deuterium to hydrogen ratio matches the values we see in certain classes of comets from our own outer solar system, it hints that planet-forming disks across the galaxy behave in similar ways. If it is wildly different, it tells us this comet was born in a very different kind of nursery. The same goes for carbon and nitrogen isotopes, slightly heavier versions of the same elements. Their ratios carry an echo of the nuclear steps that built them inside the parent star and its birth cloud. With a good spectrum, you can read that history from 500 million kilometers away. Another major target is the comet's rhythm. As 3I Atlas rotates, different patches of its surface roll into sunlight. Active vents fire, then cool. That can make the overall brightness rise and fall in a regular pattern. By monitoring its light night after night, telescopes can measure that flicker and turn it into a rotation period. Maybe the nucleus spins every few hours. Maybe it tumbles more slowly. Either way, the pattern of brightening and dimming tells us about shape, about how many jets dominate, and whether the object is stable or wobbling. Linked to that is the question of fragmentation. Comets are fragile. They are more like piles of dusty snow than solid rock. When they pass close to the sun, thermal stresses can crack them apart. Some fall into a graceful chain of fragments. Others crumble into clouds of rubble. Earth-based images in December will be sharp enough to reveal whether 3I Atlas is still one intact nucleus wrapped in a coma, or whether it has started to split into pieces. If it has broken, then each fragment becomes a mini laboratory, exposing fresh interior material that was shielded for eons. Astronomers will also keep a close eye on the comet's path itself. We know the gravity of the sun and planets will pull it along a very specific curve. On top of that, jets of gas can act like tiny thrusters and produce what are called non-gravitational accelerations. This happened with Oumuamua and became one of its biggest puzzles. For 3I Atlas, better tracking from multiple observatories in December means we can measure those tiny deviations much more precisely. If its motion matches what we expect from ordinary outgassing, that strengthens the natural comet case. If it does something smoother or stranger, the debates will flare up again. On the speculative edge of this campaign sits radio astronomy. So far, 3I Atlas has behaved like a normal comet in radio frequencies, which is to say it is mostly quiet except for natural emissions tied to molecules in its coma. If anything about the December data hints at unusual structure or unexpected acceleration, you can bet that radio telescopes will listen even more carefully. The chances of picking up anything artificial are slim. Still, the presence of instruments like Meerkat and the big dishes of the Very Large Array means that if there were something odd in radio, we would have a shot at catching it. Hanging over all of this is a simple fork in the road. When the December observations are analyzed, they will either pull 3I Atlas gently toward the center of the comet family, or they will push it farther out onto the fringe. A perfectly ordinary set of spectra and light curves would not make this story boring. Even then, we would have a clean, detailed case study of a comet from another star system, frozen chemistry from an alien dawn. But if the isotope ratios are wildly off, or the rotation pattern makes no sense, or the non-gravitational push refuses to match any realistic jet configuration, then the questions Avi Loeb and others are asking will become much harder to dismiss. For you, watching from the outside, December is more than a calendar note. It is the moment when this story opens up from space agencies and universities to anyone paying attention. Some of the telescopes collecting data will be on mountaintops, some will be in backyards. Images and spectra will flow onto the internet. Preprint papers will pop up as scientists race to interpret the numbers. Whether 3i Atlas settles down into the box marked unusual comet or stubbornly keeps 1 foot in the unknown, this is the chapter where you can watch science happening in real time. In the next part, we will zoom out even farther and place this visitor in the wider parade of interstellar objects, and in the coming era when spotting travelers from other stars becomes routine instead of rare. To really understand what 3i Atlas means, you have to step back from this single comet and look at the pattern unfolding behind it. A decade ago, interstellar objects were still mostly theory. Textbook diagrams showed star systems flinging debris into the galaxy, but it felt abstract. Then Oumuamua arrived and turned that idea into a real point of light in our sky. 2i Borisov followed and showed us a more familiar kind of visitor. 3i Atlas is now the third act in that story. The question hanging over all of this is simple. Are these rare cosmic flukes, or the first hints of a future where visitors from other stars become part of everyday astronomy? Before Oumuamua, models predicted that other star systems should be constantly throwing out small bodies as planets form and migrate. Giant planets in particular are efficient gravity machines. They kick countless icy leftovers onto escape paths. If that picture is right, then interstellar space is not empty. It is full of wandering comets and asteroids drifting between stars. The catch was that we did not have the instruments to see them. They were too faint, too small, and moving too fast for older surveys. Oumuamua changed that in 2017. A weird, flickering object barreled through, already on its way out before we realized how unusual it was. We got a handful of weeks to stare at it. Then it vanished for good. It left behind more questions than answers. 2i Borisov in 2019 was kinder. It behaved like a classic comet, giving us a clean example of a natural interstellar visitor. Those two objects together were enough to prove the basic idea. The galaxy really is sending us samples. 3i Atlas takes that proof and stretches it. The key difference with 3i Atlas is not just its brightness or activity. It is the depth and breadth of the dataset. Mars orbiters, a rover on the ground, solar observatories, asteroid missions. Soon, a full suite of Earth-based telescopes. We are not looking at a few streaks on a handful of images. We are assembling a multidimensional portrait of a foreign comet as it moves through our neighborhood. That sets a new bar for what we expect from future interstellar visitors. And there will be more. Surveys are getting better fast. The Vera Rubin Observatory, when fully online, will scan the entire visible sky every few nights with a huge digital camera. It will see faint moving dots that older systems simply miss. Predictions suggest it could find dozens of interstellar objects every year. Some will be tiny, some will be big, some will skim past the Sunday. Others will cruise through the outer system. 3i Atlas may one day feel like just the early chapter of a much thicker book. That future has two consequences. The first is scientific and comforting. Once you have a large sample, individual weird cases stop carrying so much weight. If you see 20 boring interstellar comets that all fit standard models, and one that misbehaves, you can start to understand whether that one is a rare but natural outlier or something truly unique. Statistics tame the wildness of small numbers. They let you answer questions like how often big objects get ejected, how typical our own comets are, and what range of chemistry exists in planet-forming disks across the galaxy. The second consequence is psychological. We are heading into an era where the universe is going to throw more strange data at us faster than ever. Survey telescopes will generate alerts by the millions. Machine learning filters will flag odd candidates. Social media will erupt around the weird ones before most scientists have even logged in for the day. 3i Atlas is a preview of that dynamic. A curious object appears. NASA and observatories race to gather data. Independent thinkers publish bold interpretations. Videos and threads polarize into camps. Natural or artificial. Hiding something or telling the truth. Learning how to think about interstellar visitors is not just about learning the physics. It is about building a mental toolkit that can handle ambiguity. Science often lives in the space between yes and no. Probably natural, but strange. Probably harmless, but worth watching. 3I Atlas is almost certainly a comet, yet it also shows us that our comet models were not as complete as we thought. That is not failure. That is progress. It is what happens every time the universe hands us a new kind of object. There is also a deeper, quieter shift happening. Interstellar visitors force us to stop thinking of our solar system as an isolated bubble. When a comet from another star streaks through our skies, the line between here and there gets blurry. This chunk of ice and rock condensed out of a different cloud of gas, around a different young star, under a different pattern of magnetic fields. And yet here it is, glowing green in our telescopes. It carries a physical record of conditions in a place we can never visit with current technology. As we collect more of these records, our picture of the galaxy will change. Instead of a map dotted with distant stars and exoplanets inferred from tiny dips in light, we will have actual material from those systems passing through our instruments. Interstellar objects become messengers. They tell us whether water-rich comets are common or rare. They hint at how often complex organic molecules form in cold outer disks. They give us clues about how many planetary systems survived violent youth and how many flung their building blocks into the void. So where does 3I Atlas fit in that coming crowd? It is the first visitor we have truly chased with a fleet. The first where we turned a whole solar system of hardware toward a single target. It is also the first where the debate about natural versus possibly engineered has played out in real time with millions of people watching. In that sense, it is both a scientific object and a dress rehearsal. It forces agencies to decide how transparent to be, how to talk about uncertainty, and how to respond when respected scientists publicly question the official line. Whether December's data settle every argument or not, 3I Atlas has already nudged us into a new mental era. We no longer live in a solar system where interstellar visitors are mythical. We live in one where they are real, countable, and increasingly observable. The task now is to meet them with the right mix of wonder and skepticism. In the final part, we will come back down from the big picture and ask what this specific visitor really means for us. For our species standing on one small planet, watching a traveler from another star blaze through and fade into the dark. Stand back for a moment and imagine the scene from very far away. In one corner of the galaxy, a small yellow star. Around that star, a rocky planet with a thin film of air and a nervous species that has only recently learned how to leave the ground. On a nearby world, that species has parked a 6-wheeled robot in an ancient crater. Above that world, it has placed silent machines in orbit. Around the star, it has scattered probes to watch the sun, to scout asteroids, to listen. Into this setup drifts a lump of ice and rock that formed around another star in another time. It does not slow down. It does not acknowledge that anyone is watching. It simply follows its path, falling in toward the sun, roaring to life as it heats up, then climbing back out. For a brief window, the geometry lines up so that the robot on the red planet can look up and see the visitor. An orbiter can pivot and take a close image. Solar observatories can watch its tail sway in the wind. Then it moves on. That is the core of this whole story. 3I Atlas is not visiting us in any human sense. It is not here to send a message. It is obeying gravity and physics, nothing more. All the drama is on our side. We are the ones holding press conferences, publishing essays, arguing over spectral lines, and staying up too late to process images. We are the ones asking whether this is natural or artificial, whether NASA is saying enough or hiding something. The comet just is. That does not make the questions pointless. It makes them powerful. When NASA calls an emergency briefing, it is not just to show off pretty pictures. It is to assert a story about reality. When Avi Loeb writes about deceptive obvious facts, he is not just courting controversy. He is reminding us that the stories we tell about the data matter as much as the data themselves. 3I Atlas sits right in the crossfire between those instincts. So, what does this visitor really mean for us? First, it is a hard proof that we now live in the future science fiction promised. A few generations ago, even tracking a comet from another star would have been unimaginable. Now we not only find it, we swing cameras on Mars toward it. We map its invisible hydrogen envelope. We watch its tails flutter in the solar wind. When Perseverance snapped that humble point of light in the Martian sky, it quietly joined one of the most poetic images in the history of exploration. A machine built to look for past life on one world, looking up at an object from another. Second, it tests our scientific character. The safe move is to shrug and say comet, end of story. The reckless move is to point at every oddity and yell alien. The grown-up move is harder. Assume the natural explanation by default. Demand strong evidence before you claim anything more. At the same time, refuse to sand down the anomalies just because they make you uncomfortable. Let the weirdness push you to refine your models instead of pretending it does not exist. 3i Atlas gives us a chance to practice that balance in public. You can watch in real time as observatories collect data in December, as teams publish preprints with their best fits and error bars, as debates play out between conservative interpretations and bold ones. You can see which claims are backed by numbers and which dissolve when you ask for details. If you learn to read that process for this comet, you are better prepared for the next big astronomical mystery, whether it is a strange signal, an odd exoplanet, or the first real hint of life elsewhere. Third, this visitor stretches our sense of place. We like to think of our solar system as home turf. The planets, the belts, the distant cloud of comets. 3i Atlas reminds us that space is not fenced. The material of other star systems does not stay politely on its own property. It wanders, it drifts. It occasionally plunges right through our sky, carrying information about conditions trillions of kilometers away. When you look at its green coma or its hydrogen halo, you are literally seeing frozen history from another sun. Finally, it is a lesson in humility and opportunity rolled into one. Humility, because no matter how impressive our instruments are, we are still looking at a fuzzy object far away, trying to reconstruct its nature from light and motion alone. Opportunity, because every photon it reflects or emits is a clue that we would never have had. If this one piece of debris had not happened to wander our way, we did not have to spend centuries flying a probe to its home system. The universe sent us a sample for free, and we were just barely ready to catch it. 3i Atlas will not stay. After its December swing by Earth, it will dim. It will slip past the orbits of the outer planets, cross into the sparse darkness beyond Pluto, and eventually fade beyond even our best telescopes. Somewhere far in the future, it may brush past another star, another system, another set of watchers wondering what it is. When that happens, they will not know that, for a brief time in the 2020s, a young technological species studied it from a small blue world and argued about what it meant. What will stay behind is not the comet. It is the knowledge and the mindset we build from this encounter. Better models of comet physics, richer catalogs of interstellar chemistry, stronger survey systems ready for the next visitor, and hopefully a public that is a little more comfortable living with real cosmic mysteries, where the answer is not a simple yes or no, but a careful maybe that invites more exploration. So keep an eye on the updates as the December observations roll in. Pay attention to how the story shifts as data accumulates. Whether 3i Atlas ends up filed away as an unusually lively comet or remains a stubborn outlier, it has already done something important. It has reminded us that we are part of a galaxy where stars share their debris, where worlds are not isolated, and where surprises drop into our sky without warning. Our job is simple and impossibly hard at the same time. Stay curious. Stay skeptical. Keep looking up.